And to measure that, we will look at these two. So let's start with the first one, the search information. So imagine how a fluid flows through a network of pipes. So we have a network of pipes. We have 3 particles here. So each particle represents a random walker on the graph. So let's say we have our 2 particles. Okay, so we're going to move them through through these pipes. So these are like particles of fluid. And what's going to happen is that at this, like at these branching points, there is a dispersion phenomenon. So it means that the probability or the flow, the fluid, the strength of the flow of this, the strength of the fluid flow will decrease. Okay, so as you split this energy across these 3 pipes, you will, and along the way, you will lose more energy, and at the end, okay, you will end up with basically less probability. So the more branches you cross, okay, the more branches you have, the more successive and sequential branches you cross on your graph, the lower basically your probability will be to take these pathways. So here, there is something to think about, which is the branching points. So these branching points are very important because these are actually our decision points, okay? So knowing how many branching points you have in your graph is very important, because when you reach this branching point, this is where you need to make your decisions, and this is where the information search happens, which means you're searching for the best way to go, okay? So here, the search information is defined as the extent of the dispersion at the branch points. So the branch points are very important in defining the search information. And paths associated with high search information are characterized by many or few branch points. So what do you guys think? Read this, okay? So the paths associated with high search information, are they characterized by many branch points or a few branch points? So high search information, it means that you need to explore more. You need to see, like, the more branches you have, what's going to happen? You will search more locally for your best options, okay, for your best option. So if you're going to explore your local neighborhood or do some searching, of course, when you have 2 branches, it's easier. You spend less energy in deciding as when you're having 3 or 5 or 10 branches, okay? So which means first, when you have many branches, your search will increase, and because you don't know which one to go, so you might choose this one and then, okay, do I choose the top one or the bottom one? So basically what it means, the more branching points you have, the more search you need to do, okay? So here, the higher the search information, it means you have many branching points in your graph, okay? So search information was introduced by Snepin and colleagues in 2005, and Trusina and colleagues also. So I'll put the references of these 2 papers in the links below. So what is information search or search information? It's basically a measure that quantifies the difficulty encountered by a random walker in identifying the shortest path between pairs of nodes as a matter of chance, okay? And the difficulty here, it's very important, is basically encoded in those branches, because something becomes difficult when you need to make decisions, right? When the path is very simple to follow, so you're going this way, so this is okay, you can follow these nodes, so you have like different nodes. So your path is very clear, it's not difficult. There is an easy flow of information here. But when you reach a branch and you have 3 nodes, so this is where the difficulty comes in, and this is why the search information basically depends on the branches, okay? Cool. Now, let's look at how we're going to formalize this mathematically. Now, consider an ordered sequence omega, okay, that a walker traverses to go from node U to node V. So we have our starting node U, and the walker wants to exactly follow this sequence in an ordered manner, okay? So we're not changing the order. Now, the search information as here is associated with this particular path going from U to V, okay? And guys, notice this notation. So for here, I'm using the reverse notation. So this means we're going from U to V, okay? Is determined by the probability P of the path omega VU that a random walker beginning at a node U reaches node V via the ordered sequence of nodes omega, okay, VU. So what is the probability here? So this is the thing that we need to define, okay? So if we define this, we can define the search information because it's determined by the probability. How do we define the probability? So if we look at this, so this is the definition, but first we have the path. So giving this path, we define the probability of, let's say we have already defined this probability, okay? The probability of a random walker going from U and reaching V through exactly this sequence. So this is what we note by the probability of omega VU, okay? So let's say this is known. Now, how do we define the search information? We define it as the negative log of the probability. Why the negative log? So keep it in mind. So when the probability is high, what does it mean here? When the probability that the walker goes from this point to this point is very high, does it mean that the search information is high or low? Low, very good, okay? So this is why we need to do the, we need to remap, and to remap we take the negative log, okay? So in this case, it means that using the logarithmic mapping, that the search information will be, when it is high, it means that the probability of a random walker traversing the path is low, okay? So it's the other way around. So because the higher the probability, so I see some confusions. Let's look. The higher the probability, the more, basically it means that there's no difficulty to decide, okay? So when you're going from this one, what is the probability to go from this point to this point? It's just, 1. It's like high, right? Very simple. But, and also for these ones. So these are like kind of deterministic paths. But when you reach this one, the probability will vary. So in this case, there is more search information. So you need to basically, when the probability is low, you don't know exactly, then the information is high. Yes?
Is it like information gain decision trees?
You can look at it that way from using a different vocabulary, but here what you can think about it that, okay, what is the probability that I will go from, like this point to this point, and then to the next one, and then to the next one, until I reach my destination, okay? So once you know the probability, which we will define in a bit, okay, then this probability, when it is very high, it means your decision is very strong. It's not difficult to decide. And when it's not difficult to decide, okay, when this local probability is high, it means you don't do a lot of search, okay? You don't need to waste your energy to search for the best options because your option is very clear, okay? So this is what it means. We're doing the reverse here. We're using the log 2 just to, because the probability is between 0 and 1. So what we're doing, we're just taking the opposite because when the probability is high, it means the, basically the S is low. So we need to reverse remap.
It's like having a high entropy.
Yes, yes, exactly, high entropy. So now, let's look at this question, and I would like you guys to think about it. I'll give you a minute. So, is the search information symmetric? Which means, if we want to go from U to V, okay, will it be the same as going from V to U? So, this boils down to answering the question, is what? The probability symmetric, right? Because the S depends on the probability. Omega UV, okay? So what do you guys think?
They are not the same.
They are not the same, okay? So basically, if I want to go from this one, from U to V, so my options are quite different, right? So here, but if you go from V to U, so the dispersion is slightly, it might be slightly different depending on the local structure, okay? So this is very important. So this probability will not be exactly the same. So it's not symmetric. So now let's look how to make it symmetric. Yes?
But if their starting degrees are equal, probability should be equal, right?
So if the starting degree is equal,
so if we delete two nodes from the U,
right?
Their probability should be same.
So yeah, so like if you think about it, it depends exactly on how you define this term, okay? Like the probability, how you exactly articulate it. But if you say that, you know, these nodes have exactly the same degree, will they have exactly the same shortest path? That is something to, like if you have a binary graph, I think, from what I think, you're right. Intuitively, I would say yes, okay? If you guys find counter examples, just let me know. But if you have a weighted graph, then it's not, okay? Because a weighted graph, you know, you will have a preference of diffusion. So then it should not be exactly the same, okay? So here, how to make it symmetric for, let's say, for undirected graphs. So here it's quite simple, right? So what we can do, we can take the average, right? We can just, you know, take the average. So this was also proposed, by Goni and colleagues in 2014. So they proposed a new search information in their research paper, and they just said we just need to average the search information of the path starting from V to U, and then U to V. Okay, so this is quite simple. So they're just averaging these two, and in this way it becomes symmetric. Okay, now how to express the probability of a random walker beginning at U and reaching V by traversing the ordered sequence omega VU. So this is important, and actually what I'm going to introduce now, it's connected to many different concepts, including the Laplacian and things we're going to see later. So this is the probability. So we will compute it to on this graph. So it's a very simple definition, actually. It's very intuitive. So we take the weight of the edge from U to from node U to node A1, for example, here. So pairs of nodes, and then we just normalize, divide by the strength of the node U. So this is the definition of the strength, and we have seen this before, guys, okay? So this is the simple definition of the strength, including the connection to node I, so self-connection, okay? And here we just multiply. So you can see that the probability only depends on two things. First, the weight of the edges, and second, the degree of the node or the strength of the node. So remember, the strength is in weighted graphs, the degree is in unweighted graphs, okay? So here, we're just multiplying these small probabilities. So each term, this term, represents the probability that a random walker located at node U, okay, travels to node A1. So in case, just saying, in case we have a directed graph, then we will use the outgoing strength. This is how we will update this definition, okay? Now, I would like you guys to compute this. So using this formula, I would like you to compute P of UA1, omega A UA1, so basically going from U to node A1. So our path is very short, just one hop. And then going also from node U to A2. Okay? Pen and paper, and let's calculate this together. So simple. So the first one is what? The weight. 4 divided by what? The strength. What is the strength? 10. Okay, so 5 plus 4 plus 1. Now what about the second one, going from U to A2? So to go from U to A2, following our like ordered sequence. So we need to go, first it's like 4 divided by 10 times. So this one, okay, so it's like 2 divided by the strength of this node. So it is 6. That's it. You guys got it. So it's very simple to compute it and also simple to code it up. Okay, so once you code it up and compute it, you can derive all the other measures. Okay, great. Now, let's look at these questions. I would like you guys to read these 2 questions. Or like, it's not questions, it's a statement, but tell me whether these 2 statements are true or false. So, for graphs where higher weights entail better information flow, edge weights should be remapped when computing the shortest path. Okay, so this is, remember guys, we looked at the remapping problem before when we explored the shortest path routing. And the second statement is edge weights should not be remapped when computing the information search. Okay, so you tell me true or false. First statement, what do you guys think? So I'll give you a minute, just read it and think about it. Who says the first one is a yes? Raise your hands. Come on, guys, we've seen this in the previous lecture. It's a yes. Okay? So this is to compute a Dijkstra algorithm, for example, on the graph. So the longest path is the most efficient path. So we need to reverse it. We need to remap and then find the shortest path using them by remapping the weights, okay? What about the second one? So I need to think in terms of probabilities. Who says yes and who says no? So who says yes? Raise your hand. Okay, no. Come on, guys. You have to decide yes or no. So basically, the search information, what does it mean? Think about it, okay? So when you have a higher probability, okay, you have less search. Okay, it means like these connections are strong. So the probability depends on the weights, the original weights. They have meanings, okay? So if you remap them in the beginning, what's going to happen? The high probability will become lower. Then it means your search information, like basically if the meaning that you had in the beginning will completely change. Okay, so the high cost will become low cost, and this is not good because the whole problem formalization will not be valid anymore. So the probability should always be computed using the original weights. okay? The probability of that walker going from a node, from this node to the other node. And I recommend you guys, to, like you can run this on a small example by hand and see what happens if you first remap them, okay? And then compute the search information. So you will see actually that everything will change because this will have high search here, but when you remap, it will have a lower search. It doesn't make sense, okay? So you cannot do that. So here basically should not be remapped. And this is very important. You need to know this, okay? Depending on the problem and the data and the meaning of your edges. So this is a yes, okay? So let's recap. So something to remember. Edge weights should not be remapped, okay? So this means when is the case? So when larger weights mean a stronger flow, edge weights should not be remapped. When computing the probability of the random walker traversing the sequence omega, since the random walker will be biased towards choosing edges with low probability. Okay, so and we don't want that. Great. So I think this is the first one. So why we're doing this? Anyone can remind me? Are you guys lost? What is the point? So what is our story? What are we looking for? Probability, strength, weight, stuff. Okay. What's the point? What is our destination? I think we're diffusing, right? We're all lost. Efficiency. Very good. So efficiency. So you have a graph, you have a network, and you want to know how efficient the structure of the graph you've built or constructed or estimated or used to model your data, okay, is efficient in, performing the task you're defining. For example, information flow, information integration, finding the shortest path between two parts, like, diffusing information along the optimal paths between two nodes in your graph, okay? So this is what we're looking for. First, we looked at the routing scenario, and now we looked at diffusion. So for diffusion, we said we need to model the diffusion process using a random walker so the diffusion process can be modeled as a random walker walking through on the graph, okay, through the graph connections. And then we said, okay, one possible measure is to do the search information. So the search information, it will give us a value, okay, and this value measures or quantifies how difficult it is for the walker, okay, to find the shortest path when it is diffusing or walking on the graph randomly by chance, okay? So this can be regarded, the search information, you guys can use it. You can say, okay, this search information, I might use it as, I might use this definition to investigate how, information flow on my graph. So you can directly use it, okay? So this is one first measure. Now we're going to look at a second measure. And the second measure is called path transitivity, okay?